just when you thought it was safe to go outside again, we have to revisit splitting and look at a little bit more complicated concepts. What do we know how to do already? Well, in theory, if we have a structure in front of us that we're looking at, the Lewis structure, for example, we are able to decide how many of the hydrogens or carbons are chemical shift equivalent, and therefore how many different sets of signals to expect. We know how to predict, using our correlation chart, the approximate chemical shift for each of those sets. And then for proton NMR spectroscopy, which of course has been our focus thus far, we can now predict the splitting pattern based on the n+1 rule. Another thing we should be able to do by now is, given integral values, we should be able to figure out how many hydrogens are associated with a particular set of signals. And then flipping everything on its head, if I have a spectrum of some mystery compound, I've run upstairs and taken an NMR, how do I pull that all together and decide just what that mystery compound is? What reasonable structure will fit the NMR data? So we already know how to do a whole lot. So why don't we just stop here? It's hard enough as it is. But wait, there's more. So, spin splitting part C, tree diagrams and more complex splitting. The book goes through the example of bromo ethane. I'm going to go through the example of this guy, vinyl acetate. They're very similar in that both of them have 3 hydrogens that are not chemical shift equivalent. In other words, H sub A here is in a completely different electronic environment than H sub B. Since we don't have free rotation around the carbon-carbon double bond, H sub A is kind of close to the bromine, whereas H sub B is kind of not so close. H sub C is really close. So we've got the same arrangement in vinyl acetate, and H sub A, H sub B, and H sub C, not to mention the methyl group over here, which would be completely separate. So, what would a proton NMR spectrum look like when we have 4 different kinds of hydrogens, particularly these 3 vinyl hydrogens that are all different in terms of their chemical shift? Well, fortunately, we happen to have the proton NMR spectrum for this molecule. And this is what it looks like. All right, ignore the insets for right now. Let's just look at this molecule and see if we can find all the relevant peaks. This one will be the easiest, right? It has no neighboring hydrogens. Right over here, a nice 3 hydrogen singlet. Let's see if that makes sense. If this is 3 hydrogens, then these integrals should all be 1/3 the height of this, and that looks about right. So these are each 1 hydrogen, 1 hydrogen, 1 hydrogen. Interesting. So I have a 4-line pattern for 1 hydrogen here, way downfield at 7.3. That's different. It's certainly not a quartet, because a quartet is 1 to 4 to 4 to 1. 4-line pattern, 4-line pattern. Well, remember, we're looking at 3 unique hydrogens. These 3 vinyl hydrogens have 3 unique signals and 3 unique splitting patterns. How do we analyze them? This is how we analyze them, with our splitting diagrams. So we're going to color code here. So we'll make this guy yellow, 7.27. So that's this guy. This one here, green, 4.57. And the pink guy, 4.88. So here's the rub. Yellow hydrogen is coupled to green hydrogen with a J value, a coupling constant of about 10 Hertz. But yellow hydrogen is also coupled to pink hydrogen. After all, they're both neighbors. The coupling constant between yellow and pink is actually quite large. It's usually anywhere between 15 and 17. According to this, it looks like it's about 14 Hertz. So looking at yellow, we can see that it is split by the pink guy here. Oops, didn't make it quite into the highlighter range. The pink coupling constant is really huge, 14 Hertz. So the 7.27 chemical shift is converted into a doublet by its coupling with the pink hydrogen. But then each of those signals in turn are split again. Now each time, this is n+1, right? Because there's only one pink hydrogen. That's why it's a doublet. And there's only one green hydrogen. So again, it's split into a doublet. This is the green coupling. So what do we have? We have a doublet of doublets. And we can do that for each signal. So our pink hydrogen is split by the yellow hydrogen, and of course it's the same exact coupling constant. But it's also split by the green one, and that's a really tiny coupling constant. You can look up all these coupling constants in the textbook or on one of the previous mini lectures. Okay, so I should make this clear that, let's call this J pink yellow, and this is J green yellow, and this is J green pink. So I should probably double color code this, but that might get a little complicated. Maybe not. It'll make it maybe a little more clear that this is coupling between the pink and the green. Or is this is a coupling between the yellow and the green. Yellow and the pink. Yellow and the pink. I'm a stifled colorer from way back. Alright, what does the pattern look like for real? Well, again, we're going to have a doublet of doublets. And I won't go into this one in gory detail because, again, your book goes through Bromo Ethane and it's the same kind of analysis. But all three of these give us a doublet of doublets. And so if we overlay our tree diagrams on top of the actual spectrum, you can see what these doublet of doublets look like. So here is this lineup. So the actual chemical shift is right smack dab in the middle, right there, 7.27. Note the big gap here, and then this is the 14.2 Hertz gap. Over here we've got the little bit teeny tiny gap between the two terminal hydrogens right there, and so those line up. But again, we have the gap, and it's going to be hard to see here. This has to be 14.7, and that should match up. Those two should have the same distance between them because they're both this big trans coupling constant. And then finally, our doublet of doublets for the 4.7 Hertz hydrogen right here. And now we have the much smaller cis coupling constant of, roughly 6 Hertz here. So there's our 3 doublets of doublets, and of course this is just our plain old methyl group next to the carbonyl. So tree diagrams are your friend. We'll look at another example of constructing tree diagrams or splitting diagrams when we look at another example from the book, butanal. And the book does a really nice job of explaining that, that middle CH2 sure looks like a 6-line pattern, but it's not. It's not a sextet, and we can understand that if we look at a splitting diagram. So we know that these guys are going to be split into a quartet n+1 by the adjacent methyl group. So there's my quartet, and each of these gaps should be roughly 7 Hertz based on what I know about regular old vicinal coupling. So that quartet is then also split by the adjacent CH2. So n+1 here is going to split into a quartet, n+1 here is going to split into a triplet. So we'll color code this. And again, it should be about 7 Hertz because it's vicinal coupling. It's next door neighbor coupling. So when we do this and draw our tree diagram, we see that they overlap. So as long as the coupling constants are virtually identical, which they often are if it's just plain old vicinal coupling, we should expect to see a 1 to 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 1. A 1 to 3 to 4 to 4 to 3 to 1 pattern where each of these gaps is the same and is about 7 Hertz. So it looks like a sextet, and it won't come as a surprise to you to see that it's often reported as a sextet, and that's okay, but it's really a quartet, not a quart, a quartet of triplets. That's the real description of the splitting. So this is not a violation of the n+1 rule. It is an application of the n+1 rule that sometimes they overlap and you get nice n+1 patterns. They're just not quite obvious as to what they're going to be. All right, what about long-range coupling? When you have an aromatic ring, as is shown in this chart on the right, well, we'd expect this kind of coupling where the 2 hydrogens are right next door, and we'll see coupling that's a little different from our regular vicinal coupling. Could be anywhere between 6 and 10. But surprisingly, these 2 are not next door to each other, and yet they couple. The reason they couple is because this is a pi system, and as we know, the molecular orbital is fully delocalized, and so these 2 hydrogens can talk to each other. Even hydrogens that are as far away as 1,4 on an aromatic system can talk to each other, aka couple. So when you have a molecule like this aromatic, we have H sub A, H sub B, and H sub C. They're all unique. None of these are chemical shift equivalent. So we know that H sub A and H sub C, they can couple a little bit, but it's roughly 0. They might not act, the coupling might not even show up. H sub A and H sub B, on the other hand, that's orthocoupling, and that's pretty high. We'll say that's around 7. And then the last but not least would be our metacoupling between B and C. That's between 1 and 3. We'll say it's 2. So given these values, we should be able to assign these 3 aromatic signals here. And H sub A is certainly the easiest one to do because based on the 2 coupling constants, if this is H sub A, we've got a big coupling of 7 between A and B, and then basically no coupling between H sub C. So we're just looking for a doublet. That would be H sub A. Now these other 2, well, H sub B is going to have a big 7 Hertz coupling constant and then a little 2 Hertz coupling constant. So this must be H sub B, where this is our 7 Hertz gap and this teeny thing is our 2 Hertz gap, which means this must be H sub C, which makes perfect sense because there's no coupling between H sub A and C, but there's still that little 2 Hertz coupling between B and C. So you see, coupling constants can give you very valuable information. The one coupling, aromatic long-range coupling, I want you to definitely be aware of, though, is this one. When you have a para-disubstituted aromatic ring, so 1,4, this pattern, where it kind of looks like a quartet that kind of got split apart, like so here's a quartet, and then you just chopped it in 2 and pulled it apart. This very symmetrical 2 doublet type pattern is absolutely, get it? Get it? Absolutely bells and whistles for a para-substituted compound. So if you see this quartet type thing, it's screaming, I tell you, para-substituted aromatic. All right, now, very quickly, I'm just going to warn you about stereochemistry and NMR. You are not responsible for this, but you may encounter it, so you need to be aware of it. What do I have here? Yeesh. I have 2 stereocenters. So what? Well, this is what. If you look at this molecule, I'd say it has 1, 2, 3, 4, 5, 6 carbons. Well, I'm showing you the C13 spectrum here. And if you'll look, we see 1, 2, 3, 4, 5, 6, 7? What's that all about? This is a C6 compound. How come I'm seeing, oh, you know what this is? That's the solvent, I think. No, it's not the solvent. What the heck? I'm in trouble here. How come I've got too many carbons? Well, it's that ugly stereochemistry. You see, this methyl group is in a completely different electronic environment than this methyl group. Egad. This one's kind of on the same side as the hydroxyl. This one's kind of on the opposite side. We have diastereotopic methyl groups, and they will show up in different places in the spectrum. The proton NMR spectrum is even worse. It's a hideous mess, all because of these 2 stereocenters. So just be aware that you're not responsible for this, but just be aware that stereochemistry makes it a lot more complex. So, I thought I'd better wrap up with a little joke. So I'm going to let you try and figure out what this is all about. And now that you've thought about it, I'm sure you can see that it's sailing, sailing over the 7 seas. Yeah, all right. Okay, I will put up one more little mini lecture on C13, although C13 is very straightforward, as is depth, so it'll be quite short, as this one is long enough, and we'll sign out right now.